Last time we got into really chapter 2, and a reminder again, chapter 1 was posted up on Canvas as a recorded lecture. Not again a lot in chapter 1, but you do need to watch that little video there and are responsible for what's in there. Also, as you probably saw, yesterday's recording also posted in the same location. So there should be a module that says recorded past lectures, and that's where you'll typically find all the recorded lectures for the lectures we do here in class and stuff like that. So last time we got into chapter 2, which is really about measurements. And and we also talked about a really important thing, which is units. Right? And remember that always accompanying a measurement should be the number and the unit. Again, as we talked about last time, a number by itself really is sort of useless, as it doesn't give anybody really a frame of reference of what the meaning of that number is. There's two major types of units that we come across. There's the English units that we kind of use here in the US. And as we talked about, everybody else sort of rolls with the metric system. And sort of in the 60s, as we talked about, they kind of comboed really the metric system, if you will, into what is sometimes referred to as the SI system, or the International System of Units. And as we talked about, it's really important to understand when you have a unit, what it is representing, right? So again, grams or something like that represents a mass. Milliliters represents a volume, and make sure that you do understand that. Now, mainly what we talked about as well is how to take a proper measurement. And remember that when you do take a measurement, there is always some degree of uncertainty associated with that measurement. And the degree of uncertainty, as we talked about, is based off of the actual scale that you're using on the piece of equipment. So remember, as we talked about, there's really two types of markings that you typically will see on any type of measuring device. And again, I call it the large markings, the ones that actually do have numbers associated with it. And here again, it is a 1 centimeter difference, as we saw when we were looking at it. And again, if we're measuring something like that. We also have our smaller markings, which are between those, and we do start counting after the last large marking. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, we have basically 10 markings between the two large markings, which means each of our smaller markings, as we talked about last time, is 0.1 of a centimeter. And again, that's going to be, in this case, 1.1, 1.2, 1.3, 1.4, 1.5, all the way up, obviously, to 2 in this particular case. Now, when we do take a measurement, as we talked about, there should always be numbers that really, there should kind of be no argument about. Everybody really should agree that it is at least so much. And in this case, obviously, here we can see it is at least 1.4. And when we do take that measurement, we should always record those. And those are sometimes referred to as all the certain numbers. But as we could clearly see, and as we talked about last time, it's not exactly at 1.4, and clearly here it's not exactly at 1.5 as well. And this is where the sort of estimation comes into play, and also really the uncertainty here. So if you kind of go right about there, again, maybe you feel it's not exactly halfway there, maybe you feel it's almost halfway. So maybe record a 4, and obviously the units. And as we talked about, that is what is sometimes referred to as the first uncertain number. And it is customary to record all the certain numbers plus that very first uncertain number when you take a measurement. And that is what does represent significant figures in a measurement. And in this particular case, this guy would have 3 significant figures, with the uncertain number, or the estimated digit, being that last significant figure. And that was something we talked about last time, which is, it's not always the last digit that is written. It is always the last significant figure that is written is your estimated digit along the way. So in this case, it would be here. Now, remember that if you are fairly confident on the smallest markings representation, you could easily figure out sort of how far you should take your reading to. And in most cases, it is usually one more place to the right of the smallest marking. But if you want to be for sure, you could take the smallest marking, divide it by 2, and that'll give you plus or minus 0.05 centimeters in this case, which will give us what's sometimes referred to as the tolerance of the measurement. It'll give you your 2 decimal places where you should take the reading, which is exactly what we did. And like I mentioned here, they very commonly want you in lab to include that in your measurements that you make. So you would record something like this as your sort of measurement that you would take in this particular case. Now, we finished up talking about the rules for significant figures. And remember that pretty much all non-zero numbers are significant. So any number that is not a zero is going to be a significant figure. Remember, we typically always start kind of left to right here and start counting. So we would count here, and this would actually be significant, significant. And I'll just make that a 6 for now. So that would be significant. And that would give us 4 significant figures in this particular case. We do have zeros, which just is problematic for some people because there's different types of zeros. There are those zeros that come before the first non-zero number, and none of those are significant because technically we haven't started counting until we hit that number there. And at that point, we would start counting. And here we do have 3 significant figures. We do have, they're not significant there, those beginning zeros. We have captive zeros, which are between non-zeros, and those are significant. So we would count here, that would be significant, significant, and significant, which would give us 3 significant figures in this case. And then we have the zeros at the end, which are sometimes referred to as trailing zeros. And those zeros at the end, as we saw, may not be significant if there is no decimal point in a number, which there isn't in this case, as we saw. They would just be that 1 significant figure. Or if we did put a decimal there, it would make all these zeros now significant. And this number here would have 4 significant figures if there is a decimal. Remember, the decimal point does not have to be right next to those zeros, but it does need to be written. So you can't just assume it's there if it's not written. So if it's not written, then it would fall under there is no decimal point, and they would not be significant in that case. And really the last thing we sort of talked about last time was scientific notation, which is a number that is between 1 and 10. And again, to some type of exponent that's either negative or positive. And that's really, again, depending on which way you need to move it to get to a number between 1 and 10. As we talked about, if you have sort of a large number, 1, 2, 3, you're going to move that to the left, and that would be a positive exponent. If you have a smaller number, we would go 1, 2, 3, 4 places to the right, giving us 2.3 times 10 to the minus 4. Probably more importantly, like we talked about last time, is the calculator part of this. And again, remember always when you punch it into your calculator, a number that's in scientific notation, you want to make sure that you do use your exponent buttons, which again, on most people's calculator is one of those 2, as we talked about, or again, if you have kind of that 2-tone calculator, you got probably a setup, something like that. Also a reminder that the negative button is not the subtract button, so you want to make sure you use the actual negative button as well when you do it. Remember that if you have these 2 buttons, you could kind of be sloppy the way you put it in. You don't have to worry about parentheses or anything like that. But if you have these, you do have to parenthesis around, right, each of the numbers that go in scientific notation. It's not really a big deal. You just got to remember how to do it correctly and just to make sure you do every number in parentheses. Otherwise, your calculator will do some weird math. Any questions on any of that stuff we talked about last time? All right, so we left off there talking about significant figures, and we really left off talking about at the end exact numbers, right? And exact numbers are one of 2 things. Things that are counted are things that are definitions. And remember that if it is a English to English definition, If it is a metric to metric definition, they will be considered exact numbers. There are a couple that was on that slide, I think, that we looked at. There were sort of a conversion between metric and English, like 1 inch is 2.54 centimeters. That's also considered an exact conversion. But a lot of times, though, if you do cross over from that metric to English sort of conversion, you do have to take into account the significant figures in that. If it is considered an exact number, it pretty much will have an unlimited number of significant figures, which means when we do calculations, you really don't have to worry about those numbers in terms of your answer and the sig figs there. All right, so why don't you take a moment here and for each of these, figure out how many significant figures you have, and then we'll talk about it. Let's see, so I will start the first one here. So remember, we're going to go left to right. And remember, you're not going to start counting right until you hit the very first non-zero. So again, all of those zeros are considered leading zeros. And sometimes people are confused because there's some zeros that come after the decimal point. So the deal with those, again, is they are still leading zeros because you have not hit the very first non-zero number. So again, because you haven't hit the very first non-zero number, you do not count those as anything other than leading zeros. So starting there would be significant. This is significant. That's significant. That is 3 significant figures in this case, those last 3. The uncertain or estimated digit in this case would be the 4 in this case. Here we have a number that's actually written in scientific notation. And as we talked about last time, when you write a number in scientific notation, all the numbers that come before the times 10 part are significant. And you should always look at sort of significant figures if it is written in scientific notation as it's written in scientific notation. What I mean by that is sometimes people, like I might have mentioned last time, will convert it into like a decimal number or a regular number and then try to look at the sig figs. So there's a reason why it's written in scientific notation with that many digits, and that's where you should kind of get your significant figures from. And in this case, that would be 4 significant figures. And again, the 0 at the end still works because there is a decimal right in this number, so that works there. Here, we would start counting here, and everybody would be significant. So that is 3 significant figures. Here, we would start counting here. This is a 0 at the end, and it is not significant in this case, as there is no decimal point written. And that would be 1 significant figure. And in this case, the estimated digit would be which number? It would be the 1 is our estimated digit in this case, again, not the 0. So we're basically saying it's somewhere between like 0 and 20, basically, is my best guess. Not a great measurement, obviously, if you think about just that big range of values it could be. Here we're going to go this way. We're going to start counting right there at the 9. We got a trap 0, which is significant. We got a 2, which is significant. And we have this 0 at the end, which is going to be significant, again, because way over there, right, we have our decimal point. So this guy would have 4 significant figures. In this particular case, it is the 0 at the end that is the estimated digit, uncertain digit. Any questions on any of those there? So we talked a little bit about measured numbers, which are basically measurements and obviously exact numbers. And again, just obviously here, if you weighed a patient, that would be some type of measured number. Again, if you had a basket that had 8 apples, that would be more of a counted number or an exact number. 1 kilogram equals 1,000 grams. That's a metric to metric conversion. So that's going to fall under the exact number. And here, the distance obviously would be something that would be measured in terms of how far it is. So now that we talked about significant figures, how to identify significant figures, we're going to kind of talk about calculations involving significant figures. And one of the important things that you do, obviously, is a lot of calculations in chemistry, but one of the important things is to try not to go crazy with the rounding. And people do it all the time. They like over round, they round too much. And people go the other way. They don't round enough. They just keep like every digit they see on their calculator, stuff like that. So in general, we do follow the normal sort of rounding rules, which means if it's less than 5, we pretty much will drop the numbers. And if it's kind of 5 or above, we do round up, which means we need to look at the number next to where we want to round. And it's really important, for example, here, if we had 13,333, and I wanted two significant figures. What should the answer be here? Bless you. So 13, anyone else? 1300, how about 13,000? So let's talk about both of them, and let's talk about first off this one. That is 13, which has how many significant figures? It does have two significant figures, so that's good. How about the 13,000 the way I wrote it? It has two significant figures as well. Now, they both have two significant figures, which meets the significant figures, but there is a problem with the 13. And just a common example, I don't know how common it is, but maybe somebody owes you $13,333, and they say, I'm going to give you two significant figures. Here's 13 bucks, right? You're not going to be super happy with them. There is a very, very big difference, right, in $13,000 and $13. So this is an example of I want to hit the right number of significant figures, and I do sort of extreme rounding here. And you never ever want to round that you actually change the meaning of the number, right? So the correct way would have been here with 13,000. 13,000 and 13,333 are pretty much the same number. Maybe I got like a $333 teacher discount or something like that, right? So you might not be upset with me if I offered up 13,000 for my two sig figs rather than $13. And that's a super common error that people make a lot, which is, again, they're just trying to focus a lot on the sig figs, which you should. But again, you got to also be careful you don't go crazy with the rounding and you change the meaning of it. By the way, another way I could have wrote this is 1.3 times 10 to the 1, 2, 3, and 4, right? Also would have two significant figures. So remember that you can write a number in scientific notation. And as we talked about last time, you could kind of really significant figures, right, based on how you write that number in scientific notation. So it's really important not to go crazy on the rounding. It's also really important in general when you're doing sort of calculations that you really should wait to round to the end of your problem, okay? So if you're going to do a problem, which we will do, where maybe you do like one calculation and you get an answer, and then you need to take that answer and do another calculation and get an answer, and then take it and do another calculation, and do an answer, and you keep using the same answer. If you round a lot after the first calculation and then round some more after the second calculation and then maybe the third calculation, what you're essentially going to be doing is moving yourself further and further away from the correct answers. So it's a really good practice not to round to the end. You should keep track of all the sig figs along the way and kind of have an idea as to where you should be rounding. Sometimes people will, for example, we just had this number, and maybe, this is technically where you should round, right? And maybe they'll sometimes put a line and maybe keep a couple of extra digits, maybe 2 or 3 extra digits, and that's a good way of doing it. And then you should clean up everything at the end to the right number of significant figures. So definitely, if you're doing multiple steps in a calculation, hold off on that rounding. Personally, for me, most of the time, I just keep rolling with the whole number in my calculator until the very end and just kind of clean it up at the end. And again, you could put little markings or just kind of places on the numbers to have an idea where you should end up at the end of it. But you definitely don't want to round extremely hardcore on each step because you will be pretty far off at the end in terms of the answer you're looking for. All right, so take a moment here, round each of these to two significant figures and see what you get. Okay, let's take a look. Again, we're going to two significant figures. So if we look here at the first one, right here's my second significant figure. That means I do need to look to the number to the right of it. And in this case, it is a 7, which means we do need to round it up. And that would get us to 36. And again, we do need the units, obviously meters in this case. Here, we would go to the 8 as being our second significant figure. We would look at the 2. And that is less than 5, which means we would drop it. But in this particular case, as we were just talking about, we cannot drop those zeros, right? Because we would definitely change the meaning of the number. Should I put a decimal at the end of those zeros? I should not either, because then it would have how many significant figures? It would have 4. Yeah. So again, you got to be careful. You could also obviously scientific notation this one as well, or even the first one if you liked. Here, these are not significant. Our second significant figure is actually the 6. And at this point here, we would look at the next one, which is a 2, so 0.0026 liters in this particular case. And lastly here, we would go here to our 2, and we have this one, which is an 8, and we would round up and give us 1.3 kilograms in this particular case. Yeah. Any questions on that there? Okay. So let's talk a little bit about determining significant figures in calculations. And really, when we do calculations, there is one of two sort of operations that we do. We either multiply and divide, or we add and subtract. And depending on what you're doing, you will do different types of things that you're looking at. So let's take a look first off at multiplying and dividing. If you're multiplying and dividing, your answer should have the same number of significant figures as the number with the smallest number of sig figs. So if you were taking 6.25 and you're multiplying by 1.2, this has 3 significant figures. This has 2 significant figures. Your answer you should get should end up with 2 significant figures in this case. So if you multiply or divide, it is always the least number of significant figures, and that is how many your answer should have. Now, if you add or subtract, we're actually looking at decimal places and not significant figures. So your answer should have the same number of decimal places as the number with the least number of decimal places. So again, if you took something like 1.256 and you added it to 3.0 and added it to 1.46, I'll try the old math there. 1 carry the 1 there. That's a strict of 7, 3, 4, 5, something like that. Here we're looking at decimal places. So we got 3 decimal places, 1 decimal place, and 2 decimal places. The smallest number of decimal places is the first decimal place, which means we should come here and our answer should be 5.7 in this case. 5.7 has 1 decimal place, but how many significant figures does it have? It has 2, which could be important if you're going to go take that and do another like multiplying or dividing with that answer. So again, it's important to keep track of it. So multiplying, dividing, significant figures is what you're looking at. And you're looking at the smallest. Adding, subtracting, it's decimal places, and you're also looking at the smallest. The reason it's the smallest is, frankly, it is the worst measurement in all of your calculation, right? So you're only as good as your worst measurement, and the one with the smallest number of decimal places or the smallest number of significant figures is essentially going to be your worst measurement, and that's as good as your calculation as you could get, right? It is as good as your worst sort of measurement. Any questions on that there? Now, if we were doing multiple things together, so let's just say we were taking like 4.25 times 1.3, and then we're going to divide it by 4, 6, 8, 9. You would do this in sort of steps, right? So clearly mathematical operation would tell you you should do what's in the parentheses first, right? So that is what you should do. Here we're multiplying, which means, again, we're looking at significant figures. So that would have 3 significant figures. That would have 2 significant figures. And technically speaking, if we did the top part of the calculation, we should really end up with 2 significant figures. So if you took 4.25 and you times it by 1.3, you technically get 5.525. Am I going to actually round at this point? Honestly, probably not. Yeah. So again, you probably want to kind of wait to rounding to the end. If you want, again, some people kind of put a little line up there to give you an idea as to, where you should be, keep track of it. Then what I'm going to essentially do is take this number on top, which is two significant figures, and I'm going to divide it by the number on the bottom, which is also what we're going to look at, significant figures. Number on the bottom has four significant figures. So really now at this point, I took two significant figures divided by this number on the bottom, which is four significant figures. My answer should end up with, right, two significant figures at this point. And if I did that, I don't know where we get here, made up numbers. We get a lot of zeros there. 0.00117829 is what the calculator displays. Obviously, at this point, we should go to two significant figures, which would be here. We do need to round up because of the 7, 0.0012, or 1.2 times 10 to the 12 minus 3, right? You could go that way as well. So again, I would keep track of it along the way in your calculation. Try not to round too much to the end, and then clean it up at the end to the right number of sig figs. Any questions on calculations there? All right, so once you, this is what you see on your calculator for each of these. Round these guys off to the proper answer here. So take a few moments and see what you get. First one, we're multiplying. So this is three significant figures is what we want to look at. This is two significant figures. So again, our answer should have the same as the least, which is 2. Here we would look at the 3 and then also look at the one next to it. And we would have to round up to 9.4 in this particular case. Next one here, we're dividing, which means we're looking at the significant figures. That is 4 significant figures. That is 3 significant figures. So again, the smallest number of significant figures is 3. This is what our calculator shows us. So we're looking at the 8. We then look at the 2 next to it. In this particular case, we do want to just drop the numbers at the end. Again, if we put zeros at the end, what happens is we now have, we have too many significant figures at this point. So again, in this situation, we would need to kind of drop those zeros at the end. Here we're adding, which means we are looking at decimal places. So we got 2 decimal places, 1, 3. Smallest number of decimal places is 1. And that is where we would look to our 3. And in this case, once again, we would drop off the rest of it. In this case, it has 1 decimal place, but 3 significant figures, right? If we need to kind of continue on and do some type of calculation. Here we have 4 decimal places and 1. Since we're subtracting, we will look at decimal places. 1 decimal place. Once again, here we're going to round up 0.6 in this case. Now, if you were adding something that had no decimal places, that is the least number of decimal places, right? The whole number. So you would take it to a whole number if you had that. Any questions on that there? All right, so we talked about this last time, sort of the prefixes that are commonly used, and again, the proper way to use those. A reminder that, again, we had something like we saw last time, kilo, which means, again, 10 to the 3. If we had 1 kilogram, that would have 10 to the 3 grams. So remember that 10 to the 3 is 1 times 10 to the 3. If you needed to punch it into your calculator, depending on your calculator, you can punch it in like we've been talking about, basically 1 exponent button 3 to punch that in. It is not the opposite way around. If you had something like nano, which is 10 to the minus 9, and 1 nanometer, there would be 10 to the minus 9 meters. Again, that is the proper way to do that. If you are converting, for example, from a prefix unit to a prefix unit, I would highly recommend you go back to the base unit and then take it from the base unit to the next unit. Sometimes people try to figure out how many decimal places should they move, places and all that, and they screw up. So for example, if we had something, just say that, for example, here, we'll erase all that there. Let's just say we had we had 2.5 kilograms, and we want to know how many centigrams that would be. So that's like a prefix to prefix sort of conversion. And the reason I would say the idea here is the base unit is grams. And the reason it's a good idea to go back to that base unit is you could very easily from this table find the centi conversion, which is 10 to the minus 2. You could also find obviously the kilo conversion we just did, which is 10 to the 3. And you can use those basically to go from kilograms to grams, and then from grams back to centigrams. And again, that's just a good approach to do that. So the couple conversions, I guess I could have left it there. 1 kilogram is our 10 to the 3 grams. We also have in 1 centigram, 10 to the minus 2 grams. And again, we can get that from that table. As we talked about last time, we can actually get conversion factors from this, and we could say 1 kilogram over 10 to the 3 grams, or 10 to the 3 grams over 1 kilogram. And from here, we could get some conversion factors, 1 centigram over 10 to the minus 2 grams, or you could flip it around. A conversion factor is really just a fraction, and we use them a lot, as we'll talk more about today, in dimensional analysis, which is how we show our calculations here. And it's a really simple way to do things, and it's just the opposite sort of way. So opposites cancel, so 2.5 kilograms. Again, as I mentioned before, although it's not really written as a fraction, you can kind of think of it like a fraction, and it's over 1. And what that tells us is the kilograms are up on top. And again, we want to get rid of kilograms and get ourselves to grams. So we need kilograms in the opposite location. So that would tell us that we would want to use the conversion factor there on the right. And that's going to get us on the bottom, 1 kilogram is 10 to the 3 grams. If I stop right at this point, the units that would cancel, because I'm going to multiply what's on the top and divide by what's on the bottom, kilograms divided by kilograms basically will equal 1, and the units basically cancel out in this particular case. I am now have grams, and because I set it up like this, I could clearly see that the grams are up on top. And that helps me get rid of grams at this point, because to get rid of grams, I need to go opposite. And I can now see I would want to use my conversion factor here on the left. It's going to put the grams in the correct location. And here, that would give us 10 to the minus 2 grams is 1 centigram. Again, we're going to continue to multiply what's on the top and divide by what's on the bottom. So here we would divide grams by grams, and they would cancel out. At this point, we would take our 2.5. We would times it by basically 1 times 10 to the 3. That's up on top. And we would then times it by 1, which we really don't need to do. We would then come back and divide by what's on the bottom, and really this is a 1 we don't really have to worry about. We don't really have to worry about dividing by that. But here we're going to basically divide by 1 times 10 to the minus 2. And again, you would want to put that in your calculator like we talked about with scientific notation. And you would divide that there by 10 to the minus 2. And you'll end up with 25,000 centigrams in this case. In terms of significant figures, this is an exact conversion, right? It is a metric to metric conversion. This is also an exact conversion, which means the only thing that we do ever when we're doing dimensional analysis is multiply and divide, which means we should always look at significant figures. And in this case, the first number is the only number we have to look at that has 2 significant figures. That is what our answer should have in this particular case as well. That is a big number because centigrams is a smaller right than kilograms. So you should have more of the smaller right than you do of the bigger, right? So again, that is how we get there. Any questions on that? So I would highly recommend that if you are going to do some type of conversion, sort of prefix to prefix conversion, take it back to the base unit, whatever the base unit is, because you could always find that conversion on a chart like this, or unfortunately at this school, you need to know those conversions, so you'll know those conversions, and you can take that. I've seen a lot of people just try to go directly from one to the other and always kind of mess it up. So it's always a good idea to kind of get back to that center base unit and come back. Any questions on that there? All right, so again, we talked about some of these important length equalities. Definitely this one we see a lot. That one does pop up, and a meter is 1,000 millimeters. But again, you do need to know those guys. Also, the 1,000 meters in a kilometer is also one that does come up a lot. Volume, as we talked about last time, definitely this conversion, it's all over the place throughout chemistry. You use it the most, I would say, as probably your volume conversion. And also, obviously, as we talked about, I think it might be on the next slide as well, our 1 cubic centimeter is a milliliter. And again, you could get a cubic centimeter, which is a volume. And you get that by taking 3 length measurements of something like that's a cube, length times width times height. And again, if you measure each of those things in centimeters, like we talked about last time, that's going to get you your cubic centimeters, which is a volume. While each of these individual measurements, like we talked about last time, they are length measurements, yeah? But when you multiply them together, you do get a volume. So I would say cubic centimeters is probably the most volume. You can have meters, decimeters cubed as well, but probably cubic centimeters is used a lot. It's used a lot with density, a lot. You see it a lot used with density of solids and stuff like that. And again, you can see here decimeters cubed is a liter, and our 1 cubic centimeter equals our milliliter. And as we talked about last time, we don't really see too much of CC, but again, in sort of health majors, there are they use that for how much medicine or maybe they're going to give somebody. When we see 1 centimeter, we're talking about a length. Again, when we see a cubic centimeter, it is a volume. Remember that this is a graduated cylinder, and you do want to look at the scaling. So for example, if we were going to make a measurement on this, we have 60 here, we got 70 there. So our large markings is 10 milliliters. Here we have 1, 2, 3, 4, and 5 markings between. So again, if we divide that by 5, each of our small markings is 2 milliliters. So that again would be 62, 64, and so forth. So this would be one of those ones, once again, that if you fell between any of those smaller markings, the best you could do is take it to where? You take the reading to a whole number. Again, if you divide that by 2, plus or minus 1 milliliter, right, would be your tolerance on this. So if you found yourself between your marking there, again, that's 52 on the first small marking, 54 there on the second. Again, between 52 and 54, the best you could do on this particular scale is 53, where the 3 would be the uncertain or estimated digit. Any questions on that there? So earlier, these definitely pop up a lot. For sure, the kilogram and gram conversion is used a lot. We obviously use an electronic balance to measure things a lot of times in the laboratory. By the way, when you're ever taking a reading that is digital, you should always record all the numbers. They're important, otherwise they would not be there. So it is also a very common mistake that people go to the balance and they put something down and it says like 54.3256 grams, and they just go like, I don't know, 54 looks good, and just record the first 2 numbers or something like that. So you should always record all of the digits on anything that's digital, because again, that's why they are there. Obviously, in an arrangement like that, the uncertainty would lie in the last sort of, in most cases, digital digit that you have there on your scale. All right. So we've sort of touched upon this, but let's officially talk about really conversion factors. And conversion factors do come from equalities. And equalities, as we saw in a couple of those examples, are 2 things that are on different scales that mean the same thing. So if you had 100 pennies, that is the same thing as $1, right? That is our equality. And no matter what equality that you are dealing with, you can write 2 conversion factors to use. You could write 100 pennies, for example, here over $1. or you could write $1 up on top and 100 pennies. So one thing becomes the denominator, the other one the numerator, and vice versa. These are our conversion factors, right? Now, will you use all your conversion factors in a problem? Probably not. Otherwise, you're undoing your calculation. Yeah. So you would just choose whichever one that you need to use. So again, the way we set this up, again, is always dimensional analysis. And then that is where we show kind of unit A. We use a conversion factor to get rid of unit A in the opposite location and end up with the unit B that we want. 100% of the time, multiplying the top, dividing the bottom. And this is really the way that you want to show it. So again, if we had something like, you know, 670 pennies, and we wanted to know how many dollars that would be, we would start with our 670 pennies. Again, we could assume if it helps you, put it over 1. That shows us the pennies are up on top. That makes our decision of what to use super simple. We could just go opposite location here, and we have our 100 pennies over our $1. And that's going to get us here. Oh, we got there $6.7, I guess, in this case. Whoops. Not all that there. We'll go $6.7 there. Not with everything popping up there. All right. So in this particular case, this is obviously going to be considered an exact conversion, so we don't have to worry about significant figures. That does bring us back to here, and the way I wrote this, it has only 2 significant figures, right? So our answer here should have 2 significant figures in this particular case, which is why we would not want to include the 0. I would say in a lot of cases when you do some type of dimensional analysis, conversion type problems, a lot of times that first number has almost the right sig figs. Not always, but a lot of times it does. And a lot of times you're using sort of equalities in the middle. So a couple of things here. We can definitely, as we saw there, write a conversion factor from any equality that we have. Here are some equalities that you should be aware of. There is the US or English sort of ones. So we have feet in inches. We have miles and feet, which is 5,280 feet is 1 mile. We have our gallons and our quarts. So I would say definitely this box comes up a lot. Probably obviously should know your volume conversion. Really, because you're at this school, you should know this entire thing. So you probably should just start this whole box here, I suppose, along the way. There's some of our normal metric sort of conversions, which definitely we use a lot. And these guys here are exact conversions that they want to use here. And that is metric to US. So if you're using any of these equalities, you can write 2 conversion factors for each of them. If you're in this column or anything that is, again, an English to English sort of conversion, that's going to fall under the exact sort of number. You don't have to worry about significant figures. Again, if you're sort of in this column or anything that would fall in that column, it also is going to be exact. But again, if you roll into this column here, you do have to, in some cases, look at the significant figures there are in the conversion factor that you're using and help you decide that. Again, except for obviously the 1 inch is 2.54 centimeters, or the 1 pound is 453.6 grams. So for example, if we were doing something like, well, let's go like this guy here. And let's just say we were moving at, or we want to go 425.6 miles, and we want to know how many kilometers that was. So once again, we want to kind of find our equality that would work, and that is obviously a direct equality that will work. This will give us 2 conversion factors, 1 kilometer over 0.621 miles, or 0.621 miles over a kilometer. And by the way, MI is the abbreviation there for miles. So if we set this up, again, doing our dimensional analysis, which is how they want you to show your work, and you definitely should set it up that way. We can see here miles are up on top, so that is going to give us miles here on the bottom that we want to use. Again, we're going to multiply what's on the top and divide by what's on the bottom. The miles will then cancel each other out. Here, if we punch this into our calculator here, we're going to end up with a number of 685.3462158 kilometers. That is definitely too many significant figures for sure. Yeah. So in this particular case, when we look at our original number, this guy has 4 significant figures, right? When we look at our conversion factor, because this is a metric to English conversion, we do have to look at the significant figures in this case. And obviously, we would not look at the 1 number. We would look at the other one that's not a 1. And in this case, that is 3 significant figures, which means really my answer in this case should have 3 significant figures. And in this case, that would take me here. So 685 kilometers would be the right one. So if you're in this sort of category or anything that falls sort of in that category outside of something that is considered an exact conversion, like the 1 inch is 2.54 centimeters, or the grams to pounds one, you do have to look at the conversion factor. And again, you would look at the number in that conversion factor is actually a number, not the 1 part. Obviously, that would be what you would want to look at. Question on that there. Now, doing these problems in dimensional analysis, as we'll talk about it, is really helpful. And besides the fact that they do want you to show your work this way in all the chemistry classes you take, it can also help you later on, as we'll talk about. You don't even have to worry about perhaps rearranging formulas. You just think about it as units and getting rid of the units you don't want, keeping the units you do want. And because all you do is multiply and divide, that's all you have to remember is opposites cancel, multiply and divide, and it will kind of rearrange formulas for you as well if you kind of take a more dimensional analysis approach rather than punching into some formulas. Any questions on that there? All right. So again, here we have this equality is going to give us 2 conversion factors. Again, just simply fractions. And we could use either one, whichever one that we need to use. We could have 5,280 feet over a mile. Our 1 mile is 5,280 feet. If we're driving 65 miles per hour, which is mph, something per something is actually a fraction. And that means that basically what that means is you could go 65 miles in 1 hour. Our 1 hour is 65 miles. By the way, obviously you should know time conversions. That was on that chart as well, right? There are 60 seconds in a minute, right? 60 minutes in an hour. And how many hours in a day? 24, right? Not 60. Sometimes people go 60 hours in a day. Too many hours, yeah. So just be careful on that. Obviously here, if we bought some gas for 305 for 91, what a deal. It wasn't much of a deal when I originally made this slide years ago, but 1 gallon gets you $3.05, and $3.05 will get you 1 gallon of gas. Now, sometimes and very commonly in chemistry, we are given things in terms of percentages. And as you may be familiar with, if you have something that is given to you in a percentage and you want to use it as sort of a usable conversion factor, it oftentimes is best just to assume 100 of whatever you have, because what that does is essentially just keeps the numbers the same. You can assume anything you want, but if you keep it 100, it'll be the same. So if I have somebody that is 12% body fat by mass, that would mean that I would have 12 kilograms of body fat per 100 kilograms of body mass. Or 100 kilograms of body mass gives you, 12 kilograms of body fat. Or for more of a US measurement, 12 pounds per 100 pounds of body fat and 100 pounds of body fat, body mass gives you 12 pounds of body fat. So again, that's like a very common way. You have some type of percentage, just assume you have 100 of something, and you can kind of convert it. So for example, if you had a 4.5% by mass solution of sodium chloride, M to M means basically mass to mass. What that would mean, for example, is you have basically 4.5 grams of sodium chloride in 100 grams of solution. So that's, again, just an easy way to kind of convert that into a usable sort of conversion factor. You could also flip it around and do 100 grams of solution over 4.5 grams of sodium chloride, and you can use it either way. So again, assuming 100 is a really good way to kind of turn something into a usable sort of conversion factor. So we've been talking about this, but dimensional analysis is 100% the way when they say in all the chemistry classes you take to show your work what they want you to show your work. And again, it is conversion factors, equalities, and really picking the best approach to get you there. Now, if it's a true conversion problem, frankly, there can be multiple ways to get to the same answer depending on what conversion you sort of choose. But the ultimate way of this is, again, you start with one unit, you get rid of the unit you don't want on the opposite location, and again, you end up with that one, and maybe you want to get rid of the B as well. So maybe you get rid of B, use another conversion factor to get to C. Once again, 100% of the time, anything that you got on top gets multiplied. Everything on the bottom here gets divided. Now, where people screw up when they do dimensional analysis problems, besides maybe using the wrong numbers or something like that, is the way a lot of times they punch it into their calculator. And what people want to do is punch the entire thing into their calculator all at once, which if you're not really careful about and don't use parentheses correctly, which in my experience, most people don't, you will get the wrong answer. And the best piece of advice in terms of calculator and punching it in is no matter how many things you got on top, and maybe you did one more as well, right? What I would do is multiply as many numbers as you want on top, and then you should hit equals on your calculator. And whatever you got on the bottom that you need to divide by, you should divide by the first one and then hit equals. Divide by the next number, hit equals. Divide by the next number and it equals, especially on the dividing part. Again, I can't tell you how many times I've seen people have a setup right, but not the right answer. And it's because of the way they punch it into their calculator. So they try to do too much at once. So again, you can take as many numbers as you want on top and multiply them, but at the end you should hit equals, come back and divide by each of them individually and hit equals after each time. You will always get the right answer if you do it that way. Again, if you try to punch it all in at once, it's not going to be good. Whatever you are trying to solve for should be up on top by itself. Yeah, so whatever you're trying to get to. So if I was trying to get to unit D, it needs to be the last one standing there, right? Up on top by itself in terms of units. Now, if I had 2 units, I need both of those units to be in the right location, up on top and on the bottom. And that is the second most common problem that people do when they do calculations. They don't do dimensional analysis correctly. They don't set it up clearly as fractions so you can see where everything's located. They do a semi-fraction. And what ends up happening is they do something like this, for example, I don't know, feet per second. They kind of put it like that. And they do the next one, maybe, you know, like feet per minute. And at some point, they don't know if there should be multiplying or dividing because it's really not set up, you know, correctly. So if you set up like I'm showing you here, clear fractions, clear top and bottom, you should know exactly math-wise what you should be doing. And that happens a lot when people have 2 units and they end up, for example, if they have something like a unit of time on the bottom, they end up like multiplying when they should be dividing or divide when they should be multiplying. So you definitely want to keep everything separated so that you get to the right answers. Now, the general steps to follow when you're doing a dimensional analysis problem is you should write what's given to you. You should think about what you want to find, and you really should think about the appropriate pathway to get you there. And like I said, if it is just a straight up conversion type problem, there could be multiple ways to get to the end answer. And they're all good as long as they're legit conversions that you didn't just make up yourself. You want to write the appropriate conversion factors, pick the ones that you're going to use. You want to set up the problem showing all the units, canceling out, and you obviously want to solve the problem. So, for example, like we saw there previously, if we had something like $3 and we want to know how many pennies, obviously we could use our example like we did earlier there. 100 pennies is our $1. That is going to give us our equality that's going to work. We could have, again, two conversion factors. 100 pennies is $1. Our $1 is 100 pennies. And that's going to be our conversion factors. And again, we're going to start with what was given to us, which is $3. If it helps you, you don't have to do it, but if it helps you, just put it over 1 so you could clearly again see dollars is on top. You want to make this as simple as possible for you. So again, opposites, all you have to remember. So dollars are on top. I need to get rid of those. Dollars need to go on the bottom. I need to use the one over here. So $1, again, 100 pennies. Dollars going to be multiplied here, going to divide on the bottom. These guys will divide out. Again, that's going to be dollars divided by dollars, which is equal 1. That's going to give us our 300 pennies in this case. Again, we don't have to look at that as that's an exact conversion. Here we have just one significant figure. One significant figure looks like a winner in this case again. Any questions on that there? So as much as you don't want to do it, you should get in a habit of doing it if you plan on continuing on with chemistry classes here, because that is what they want you to show. Yeah. And definitely when they say show your work, that is sort of what they want you to show it like that. All right. So let's take a look at some here. Why don't you try this? I'll give you some equalities that might work, and why don't you see what you end up with here. You go to AM PM, you get yourself a 32 fluid ounce drink of Diet Coke from the Thirst Oasis. How many gallons of Diet Coke did you drink? There are some equalities that might be helpful for you. So why don't you take a few moments there and see what you come up with here. Maybe finding some, obviously here we could go from fluid ounces to quarts. And then we could take quarts basically over there to gallons as a pathway. The 4 available sort of conversion factors to you, obviously we're not going to use them all. We're going to use whichever ones are necessary. We're going to start with what was given to us, which was 32 fluid ounces. Once again, if it helps you, just put a little 1 over it. And again, now we can clearly see fluid ounces are up on top. So when we go to our choices here for our first conversion factor, all we have to remember is opposites cancel. So that puts fluid ounces in the opposite location, which is the bottom. And that'll put 1 quart up on top, 32 fluid ounces on the bottom. If we stop right at this point, the fluid ounces on top and bottom will cancel each other out. The only unit we're left with at this point is quarts, which again, we could clearly see is up on top. So that makes it a no-brainer here on our next conversion. We also need quarts to get rid of, so we need it on the bottom. So again, opposites cancel, and that will give us 1 gallon is 4 quarts. Again here, the quarts will cancel each other out. Once again, by setting it up as dimensional analysis in terms of the math, you don't even have to worry about should I be multiplying and dividing, because all you have to remember is top gets multiplied, bottom gets divided. So it even takes the should I multiply or divide sort of question out of it for you when you set it up like this. So here we're going to go 32 basically times 1, which we don't have to pretty much do. Hit equals. We're going to divide it by our first number on the bottom, which is 32, hit equals, divided by our second number on the bottom, which is 4, and hit equals. And it does give us 0.25 gallons. It does not give us 1 over 4 gallons, because that makes me think you're just too lazy to hit the divide button, yeah? So don't give an answer in a fraction. Give it as a number, decimal to the proper number of significant figures. Not super bad in this case, but I've had people write answers like 325 feet over 4,262 hours, looks good, right? So don't leave an answer like that. In terms of significant figures, pretty much exact here. We don't have to worry about it exact. That does default us back to our original number in terms of significant figures. Again, as I mentioned before, the other kind of beautiful thing of dimensional analysis is it's multiplying and dividing. So all you have to remember is sig figs is what I should think about in terms of my answer. And that is 2 sig figs. And that is 2 sig figs right about there. Yeah. Any questions on that there? All right. It comes as 250 milligrams per 5 milliliters. So very commonly in problems, you are given a sort of conversion factor, if you will, in the actual problem itself. And that is 250 milligrams per 5 milliliters. We could actually use it like I have it written there. We could also, if we needed to, flip that guy around. And again, here we have in this case now really a direct conversion to go from milligrams to milliliters. So we'll do our dimensional analysis here. We'll take our 500 milligrams. Again, if it helps you, you could do a 1 there. Milligrams are clearly on top, which tells us we actually do need to use it in this kind of flipped version here. And that's going to give us 5 milliliters over 250 milligrams. Once again, we're going to multiply what's on the top, divide by what's on the bottom. That's going to get rid of the milligrams that we don't want. This is the only unit that's left, which is actually what we do want here. So we're going to go multiply 500 times 5, hit equals, divide by 250. And that's going to give us 10 milliliters. Now we do want to kind of think about significant figures here. So in this particular case, and probably most cases, if you're given a conversion factor like we were here that's in the problem, that's really not going to be considered an exact conversion. So you really should look at the numbers that are there. So sig fig wise, that has 2 sig figs, right? This guy has 2 sig figs, and our original number actually has 3 sig figs, as there is a decimal point there, right? That tells us here, again, we know we're dimensional analyzing, which is multiplying and dividing. So it's always significant figures. So that means 2 significant figures is really what we need. So I do actually perhaps need to put a little decimal there. That's going to make that 0 at the end significant and give us 2 significant figures. You could also, if you want, in scientific notation, 1.0 times 10 to the 1. And that would also obviously give you 2 significant figures as well. Any questions on that? So a lot of times you're given conversions really in problems. And in that case, obviously, usually you should look at the sig figs in those as you're doing that sort of calculation. Any questions on that? Okay. All right, so a patient receives 5 pints of plasma. How many milliliters of plasma did they get? A couple of qualities, some conversion factors that you could maybe use. So give it a go, set it up dimensional analysis, see what you come up with. Okay, so let's take a look, see how we're doing. So again, when you have a conversion problem, as I mentioned before, there could be multiple pathways. Ultimately here, we want to go from pints to milliliters, and my pathway here is going to go pints to quarts, and then quarts to milliliters. So again, there could be alternative pathway, and again, it should get you the same spot regardless of sort of which one you choose. So once again here, I'm going to start with what was given to me. I'm going to think of it as like a fraction, top and bottom here. Again, I know I need to get rid of pints. So pints are clearly up on top, so opposites cancel. So that is what I'm going to roll with here. A quart is 2 pints. Once again, if I stop the calculation right at this point, since those units are opposite of each other, they will cancel each other out. Again, setting it up this way, I could once again see quarts are clearly up on top. And again, to get rid of it, I need them on the bottom. And that is going to be our guy here on the right. And you could just continue on with the calculation. If you want to get an answer, you could. They typically want you to kind of continue on with the calculation here. But if you do want to get an answer after the first one, that's perfectly fine. Again, I would not round like we talked about. I would keep a couple extra digits and then continue on. Here, the quarts on top and bottom are going to cancel. And again, as we know, we're going to multiply our top. We're going to divide our bottom here. So we're going to take our 5 times our 946. We're going to divide it by 2. And that's going to give us 2365 milliliters on my calculator, as that's the only unit left. Now we do need to take a look at some sig figs, right? Our original number had 2 sig figs. That is a pint to a quart conversion, which I don't have to worry about, right? It's exact. How about this one? That is a quart to a milliliter. Should I worry about that one? The answer is yeah, that is English to metric conversion, right? So here we would worry about this number, which is 3 significant figures. So our smallest is actually 2. So this should get us to 2400 milliliters. As we have to go here, look at the 6 and round up. Or again, you could scientific notation it. That looks something like this as well. On the scientific notation, we do need to drop the zeros because if we kept the zeros on scientific notation, we would then have 4 significant figures. So we definitely have to do that. Yes, sir. Yeah, so for the most part, the 2 places you have to worry about is what you just said, basically English to metric conversion, except for those couple that we talked about that are still considered exact, like 1 inch is 2.54 centimeters, or the here, even though it's not really, but they use the 1 pound is 453.6. Those are considered exact. So if you did one that was 1 inch to centimeters as a conversion, even though it's metric to English, it's considered an exact conversion. So you wouldn't have to worry about that. But all other pretty much metric to English, you should. The other place where you should worry is like we saw in the previous problem, if you're given something in the actual problem, which is not this like a regular conversion or something like that, that you should also look at. And those are really the 2 places. I would say almost 98% of the time, you could almost bypass a lot of the conversion factors that you use because a lot of times you are sticking kind of like English to English or metric to metric in a lot of cases. But that's really what you should look at, those 2 situations. Other questions? Go. Oh, by the way, sometimes people ask, what do you need to show for work, for full credit, by the way. Now, for me, for full credit, what you would need to show is pretty much this bottom part. Yeah. The setup with the dimensional analysis, the conversion factors used, the units canceling out, the answers to the proper digits. You don't necessarily have to, for me, kind of show all the top part here. If it helps you to do it for yourself. I don't care if you show it or not, you can. But minimum for full credit, you'd have to show the setup on the bottom with the answer to the right number of sig figs. Any questions on that there? Okay. All right, let's try one more here. Maybe you are stranded 125 miles away from home, no money. You decide, hey, it's a nice day, except for yesterday. There was a lot of rain and lightning and thunder. It's quite scary. Um, if you walk an average of 55 feet per minute, how many days is it going to take you to get home if you don't stop? Because maybe it was raining, lightning, and thundering. I don't know. Let's see. All right, so take a few moments there, set it up, see what you come up with here. Distance to time, and that's what we're ultimately looking to find, which is days, which is a unit of time. So in this case, we could use it as 55 feet per minute. We could flip it around and use minutes on top and 55 feet on the bottom. Remember, when you see per, it's 2 different units, right? Something over something. We also do have a little bit of a unit issue, which you always want to be aware of. Remember that things will not cancel out correctly if they are not in the same unit, right? So here our distance is in miles, but my rate distance there is in feet, which means you do need to do one of those conversions. You can either convert the miles to feet or the feet to miles, but you can't use them like they are, just like that, 1 miles, 1 feet. It will not cancel out correctly. I'm going to convert from miles to feet, so I could just use the kind of conversion factor the way it is. So what I'm going to first do is take my 125 miles, And I'm going to find obviously my equality here. That gives me my conversion factor. And just like before, I'm not going to overcomplicate it. I'm going to do a dimensional analysis, keep it like a fraction. I want to get rid of miles, which means the miles part of my equality should go on the bottom and the feet part of my equality should go up on top because that is what I'm looking to solve for. The miles here will cancel, and that's going to give us 125 times 5280. And that's going to give us 660,000. Did I get enough zeros there? I think I did. And these are going to be feet. Now that I have this in feet, I should have no problem using it with my conversion factor. And obviously, you could have done the feet per minute to miles per minute if you wanted to. I'm going to take that whole number there. And again, setting it up so opposites cancel. Feet are on top, which means I need feet actually on the bottom here. So I need to use that kind of conversion in the reverse direction there. Again, opposites are going to cancel out for me here. And this is the move that's going to take us from distance now into a unit of time, right? And that is what we're ultimately looking for, which is days, which is unit of time. At this point, it is our minutes to days that we hopefully won't mess up here. So we'll continue on. I could clearly see minutes are on top. So to get rid of minutes, it needs to go on the bottom. So 60 minutes on the bottom gives me 1 hour up on top using this equality and obviously the conversion factor that comes from it. Minutes will cancel. If I stop right at this point, I'm in units of hours, which is close to where I need. And here it is, our 24 hours in a day, not 60. There we go, hours in a day. I can't tell you how many tests I've seen 60 on. And again, we're going to go opposites here. So hours on top, we need it on the bottom so that they cancel. This leaves us, as we were talking about, the proper unit by itself up on top, which is what we're solving for. So again, typically speaking, if you need to solve for something that is just one unit, it has to be up on top by itself. Because if I had the unit on the bottom and I solve for it, what am I really solving for? 1 over days in this case, right? And it's the reciprocal. So it cannot be on the bottom. So that's a good way. If you set it up like this, you will understand hopefully what you get. Once again, dimensional analysis. So we're just going to multiply the top and bottom all the way across. In this case, I'm going to take the 660,000. Pretty much everything on top is 1, so I don't really need to multiply. If you want to, you can, I suppose. I'm going to divide by the first number on the bottom, which is 55. I'm going to hit equals. I'm going to divide by the second number on the bottom, 60, and hit equals. And I'm going to divide by the last number on the bottom, 24, and hit equals. And that's going to give me 8.3333, lots of threes, days, right? Now, in terms of significant figures, we do want to think about the entire calculation. So technically speaking, we started over here with the 125. And this guy has 3 significant figures. So even though here I really wrote it as 2 significant figures, this guy actually should be 3 significant figures, right? And that means that technically this guy should be 3 significant figures. This guy is actually 3 significant figures because I do need to look at it because it came from the problem. This guy is technically 1, which is the number I don't really need to look at. And this is an exact, that's an exact, which means actually we should probably end up over here at 8.33 days are 3 significant figures. Any questions on that there? Yeah. I'm sorry, say it again. If you put what now? 8 days, 19 hours, 2 minutes, I'm going to say technically it would be wrong in the sense of you always want to answer what the question is asking. So in this case, it's just straight up asking days. So that's always a good rule. Just follow exactly what the question is asking and end up that way. Is it wrong in terms of maybe the right? I'll trust you on the hours, the days, and seconds, whatever you got there. But it may be correct in terms of the number. But you definitely always want to answer kind of what the question is asking for and leave it in kind of those units, if you will. Yeah. Yeah. Are you asking about how we got to the significant figures on the answer? Is that what you're asking, or? Yeah. So basically, obviously up here, we multiplied, and it's always the same calculation regardless. So it's always multiplying the top, dividing the bottom. And in this case, we got an answer that I actually got an answer instead of just doing all one move. So I took that answer down here, and again, technically speaking, you would multiply all the way across the top. And then I would hit equals if you actually had numbers up there, for example. And then you're technically going to divide across the entire bottom. But I would definitely do each one individually. That will always get you to the right answer, and kind of use the equal sign. Don't be afraid to use the equal sign a lot. It's super common. Like I said earlier, people try to punch it all in at once, and a lot of times get the wrong answer. Yeah. 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 So it technically would be something that you would want to look at because it was given to you in the problem. Not every rate is going to be exactly right, 55 feet per minute. So somebody else could be walking 60 feet per minute. So it's not like always, for example, 12 inches is always a foot, right? No matter what you do. So in this case, it is specific for this question. It is specifically specific for this question, but it's not like a true equality, if you will, like 12 inches is always a foot no matter what the situation is. So that's why we would look at it here. And in terms of analyzing, we would look obviously here and obviously back here at these two. These guys over here would be considered exact numbers because again, no matter what day it is, there's only 24 hours, right? And there's always 60 minutes in an hour and stuff like that. So those are always that. So that's why if we have some type of conversion in the problem, we typically would look at the numbers that are associated with it. Yeah. Yeah. So basically, in terms of conversion factors, I would say the two things you should really take a look at it is if it is listed in the problem and it's not like, a true, like, for example, we had one listed where it was like the pints to milliliters, which is a true conversion. But, if you have something like this that's in a problem that you're just kind of using specifically for that particular problem, you should look at it. And if you're crossing over from English to metric, that's typically what you should use. The final answer would be, yeah, it would be two in that case, which years ago it used to actually say 55 feet per minute. I put the decimal in later, but you'd be correct. You would look at that and you would go to 8.3 would be your answer. Yeah. Yep. Other questions? All right, let's try just maybe a couple more here just to make sure. And why don't you try these guys and see what you come up with? Let's say you had you're traveling 65.5 miles per hour, and I want to know how many it's feet per second that is. And why don't you also do this one, which is 325 cubic centimeters. I want to know how many cubic feet that would be. Let me give you some stuff that might be helpful. Let's do, actually not miles, I'm sorry, I want kilometers per second on the first one. Let me do, not feet. Actually, let's do kilometers per second. All right, so 1 mile is we used that one earlier there. Yeah, we'll just use this one. Why not? Do 1.61 kilometers. Or you can use the previous one that we saw as well. That should work. And the rest you should know. And then obviously 1 inch equals 2.54 centimeters. Remember, you do need to know these guys, right? Maybe 12 inches is a foot, right? All right, so see what you come up with here. Okay, let's take a look, see how you're doing. We'll start with the first one. So 65.5 miles per hour. So that's basically 2 units. We basically have miles per hour, and we essentially need to end up with kilometers per second. So again, you definitely want to set this up to dimensional analysis way. By just doing so, we can see basically on top, we got to go miles to kilometers. And then I can see on the bottom, I need to go hours to seconds. So it's definitely how you want to set it up so you can clearly see where the units are. Again, super common error people make is not knowing what they should be doing, multiplying, dividing, all that. So we're going to start with our 65.5 miles over an hour. And I'm just going to do one conversion at a time. So I'm going to start with the miles and take it to kilometers, which I do have a direct conversion to do so. You can use either one. They're both the same. By the way, you get the one on the bottom by taking 1 divided by 1.61, and that basically turns it over that way. So I'll use the one I think that we used before. I am still going to do opposite. So miles is on top. That means I do need miles on the bottom. And kilometers in this case would be on top. At this point, if I stopped, the miles would cancel. And the units I'm in right at this point are kilometers per hour, right? And frankly, I'm halfway there pretty much. I got the top part good to go. Now, clearly, the way it is set up, I can see that hours, which I need to get rid of, are on the bottom, and I need to get eventually that to seconds on the bottom. So that's going to help me with my next conversion, which is 1 hour on top to go opposite, right? Gives me however you want to do it. You could go 60 minutes on the bottom. That is going to give me the proper way that those guys are going to cancel. Again, we have hours on top and bottom. If I stopped right at this moment, what units am I in? Yeah, kilometers per minute. And again, I could clearly see I'm close to what I need, but I need seconds on the bottom. And I can see minutes are still on the bottom. So that's going to help me do the next conversion, which obviously is a minute. There are 60 seconds in a minute. So we could use that. And again, opposite. So minutes I want to get rid of, which means minutes need to go up on top. Seconds need to go on the bottom so that they do cancel. I am now left with kilometers per second. And the nice thing about setting it up like this is I didn't have to think too hard about where to put things, right? Opposites cancel. The actually really nice thing about this is now I don't have to make those decisions of should I be multiplying or dividing because I know automatically everything on top gets multiplied and everything on the bottom gets divided, right? So again, it takes care of the math part of it for you without you having to worry about it. We're gonna go 65.5. Honestly, everything on top's 1. So if you want to do it, you can, but you don't really need to. You could hit equals. We're gonna divide by the first number, 0.621. I would hit equals after that. I would divide by the next number, which is 60, and hit equals. And divide by the last number, which is 60 as well, and hit equals. That is gonna get me 0.029298622. The units stay like this. The top unit gets the number. The bottom unit does not have a number typically. We obviously need to clean it up because that's way too many significant figures, right? So when we look at this, we definitely have to look at the first number, which is 3. This is an English to metric conversion, which means 3 sig figs looking at that number. This is an exact we don't have to worry about. That's an exact which we don't have to worry about, which means we should end up 3 looks like the winner, no matter which one you look at. So that's going to get us something like 0.029. And when we need to look at this number and round 3 kilometers per second. Or if you want to do a scientific notation, 2.93 times 10 to the minus 2 kilometers per second, if you'd like to do it that way. Any questions on that setup there? So again, I can't tell you how many people would do this problem and multiply the 60s at the end there. because they didn't set it up correctly, and they kind of fakely set it up, right? And they don't know if there should be multiplier and divide. So the idea here is you want to make it as easy as possible for you, right? A lot less thinking sometimes is better. And again, if you set it up this way, all you have to remember is three things: opposites cancel, multiply the top, divide the bottom. You'll be in business for most of the calculations. Any questions on that one there? Take a look at the bottom. We're going from cubic centimeters to cubic feet. By the way, what type of units are those? Those are volumes, yes. So again, they're cubic lengths, so these are all volumes. So I could go really, even though I kind of wrote over it all there, I could go from centimeters to inches to feet, and that will get me there. I could use my regular sort of conversions to do that, or equalities. So I'm going to start with my 325 centimeters, cubic centimeters. I'm going to put it over 1. I'm going to do my conversion opposite, which means centimeters on the bottom. So 2.54 centimeters on the bottom is 1 inch. By the way, how many centimeters cubes does that get rid of? Only 1, by the way. So technically speaking, you need to do it not once, not twice, but you actually have to do it 3 times. And when you do it 3 times, centimeters times centimeters times centimeters is the cubic centimeters. They cancel that out. By the way, up on top, what am I left with right now in terms of units? Yeah, in terms of units, I have cubic inches up on top, right? Inches times inches, which means as I go from inches to feet, I actually have to do that conversion 3 times as well, right? So I got to go 12 inches on the bottom is 1 foot. 12 inches on the bottom is 1 foot. And left just enough room. 12 inches on the bottom is 1 foot. Inches times inches times inches is cubic inches. That takes care of my inches times inches times inches. If I multiply it up on top there, that is feet times feet times feet, which is cubic feet, and that is what I'm looking for. So that's a big thing there. 325 basically times 1 divided by 2.54 hit equals, divided by 2.54 hit equals, divided by 2.54 hit equals, divided by 12 hit equals, divided by 12 hit equals, divided by 12 hit equals, and you will end up with 0.0115 cubic feet in this particular case. Or again, if you want to do scientific notation, 1.15 times 10 to the minus 2 cubic feet. Now, do you have to show it like that? I personally would recommend doing it that way because, as I've mentioned before, I've seen a lot of things over the years, and I've seen people do this. And actually is perfectly fine, except that when most people go to do that, they never live to actually cube the numbers. They just cube the units, and they just do like 2.54 once and the 12 once. So it is absolutely correct. You can set it up like that. It's perfectly fine. If you do, just remember to actually do the math correctly, and you have to actually do it 3 times. Sometimes maybe it's better just to see it that you need to punch it in there 3 times, but it very commonly, people will always want to like cube the units, but never the number and stuff like that. So you absolutely could set it up like on the bottom, and it'd be perfectly fine as long as you did the math correctly. Question on dimensional analysis, conversions, equalities. As we mentioned before, you do need to kind of know the equalities. They will not be provided for you. And again, that table is probably a pretty good one. It has a lot of the ones that probably commonly you'll come across that we saw earlier. Also, obviously, the prefixes as well, right? You need to know the kilo, the centi, and those type of things. Any questions on dimensional analysis or anything like that? Okay, the next thing we're going to talk about, which is actually the last thing in this chapter, believe it or not, is density. Now, density is defined as the amount of matter that is present in a given volume of a substance. And the differences in density, for example, determines, for example, if something will sink or float, like in water. So if we take something like water, if something is more dense than water, it typically will sink. And if something is less dense than water, it will float. And In general, things in their solid state are usually more dense than in their liquid state. The one notable exception is water, actually. Water in its solid state is less dense than water in its liquid state. That is why when we put ice cubes in our cup, they end up on the top of the glass, right? They float in it, and they're actually less dense than water. As we'll talk about in a later chapter, what happens when water comes together to make ice is they can't get very close to each other in the solid state. So there's a lot of really empty space between the water molecules. And it actually makes the density of solid water, which is ice, less than liquid water. By the way, density is a property that does change with temperature. So if you change the temperature, you can change, or you will have a different density as well. Speaking of density, there are typical units associated with density. And those units are grams per milliliter or grams per cubic centimeter. And these are pretty much the units that you will see. Grams per cubic centimeter are grams per milliliter. And remember that a milliliter is the same as a cubic centimeter. And this is typically what you see for solids and liquids. For gases, although we don't come across it too much in this particular class, but if you go on to 1A, you will. Typically, we give gas density or density of gases in grams per liter. There is a formula for density, which is D is equal to M divided by V. That is mass divided by volume. And that is where those units come from, grams per milliliter or grams per cubic centimeter. You can rearrange this equation to solve for any of those three things. The volume would equal the mass divided by the density, or the mass would equal the volume times the density. And it's very common to solve for any one of those three things. Sometimes people like to remember that as like the DMV triangle. Everybody loves the DMV. Density is mass divided by volume. Volume is mass divided by density. And mass is density times volume. So that's a way you could kind of quickly remember it. The density of water, liquid water, for the most part, if you ever need to use it, is 1 gram per milliliter, or again, 1 gram per cubic centimeter. Now, as I mentioned a second ago, density does change with temperature, but I would say probably 99% of the time, even maybe more, if you come across a problem and you feel like I need the density of water and it's not given to you, 1 gram per milliliter is probably the safe bet to use. Again, it does change with temperature, but that's almost like a constant value, and you definitely should know that one as you go through. Yeah. So why don't we try one here? A block has a volume of 25.3 cubic centimeters. Its mass is 21.7 grams. What is the density of the block? Okay, so let's take a look. And a really good thing to do in this problem, and really a lot of chemistry problems, is sometimes it's a really good idea just to kind of pull out the information from the problem, label what it is, and a lot of times if you know some formulas, you could probably narrow down which path to take. So clearly we have a volume that is 25.3 cubic centimeters. By the way, that is a volume you probably got by taking like length times width times height like we talked about previously. The mass here is 21.7 grams. So I have volume and mass, and I'm looking for densities. So really I have everything I need in this particular case just to plug it in. And we will go 21.7 grams divided by 25.3 cubic centimeters. And we pop that into our calculator here, a little 21.7 divided by 25.3. Going to get us a 0.85. And again, on our calculator, we're going to get this displayed on it. And obviously here we want to think about significant figures. So in this case, we're actually dividing. So again, we're going to be looking at sig figs. And that's going to have 3 sig figs. That's going to have 3 sig figs, which means we are going to go here. We would look at this guy and we would round up in this case, and that would get us 0.858. Once again, this unit on top and this unit on the bottom do not cancel. So they both remain the same and they both stay in the same position. So the number always goes with the top unit. And the bottom unit is assumed to basically just be 1, although we don't usually write the 1. It's just assumed basically it's the 1 on the bottom there. And we would have something like that there, 0.858 grams per cubic centimeter. And again, yeah, it would be because it really is the same. Again, in this case, you probably would want to keep it as cubic centimeters since that was the sort of volume unit in it. But because it's a one-to-one conversion, it really doesn't change the number or anything like that that you'd have. Other questions? So let's talk a little bit about volume and how we get volume. So we talked about a couple of ways that we could get a volume. Clearly, one way we could get a volume, like we talked about last time and this time as well, is we could just simply just take a reading, basically, right? And you could just take an actual reading using something like a graduated cylinder or whatever you may be measuring in. As we just saw in the previous problem we talked about previously, if you got some type of square block or cube, you could take 3 length measurements. And again, like we saw there, if they are each in centimeters, that will give you your cubic centimeters, which is a volume. Now, the third way that we could get a volume, and very, very common in density, especially if you have a solid object, is what is referred to as volume by displacement. And volume by displacement basically is what it sounds like when we put a solid object into a liquid like water. It basically will displace a volume that's equal to itself. So for example, here, before this lady comes and jumps into the pool, we have an initial volume basically of the water level that's in there. Once she goes into the pool, she's going to displace the water and it's going to rise in this case to a final volume. If you take the difference between the water level where it started and where it ended, that is basically the volume of the object. So in general, you could find the volume of an object by taking the final volume minus the initial volume. And that is like a super common way that you could find the volume of an object. You'll do that tomorrow in lab. You'll throw some stoppers into some water. You'll read the volume before and after. And that will give you obviously the volume of like the stopper and stuff like that. So it's a super easy way to kind of figure out the volume of an object. Any questions on that there? Say again? So it's a good way as well. Yeah, if they have kind of like a weird shape as well. Yeah, it's obviously if you have something like a cube, you could measure it, but you could also do it with a cube if you had a bigger thing to drop it in and stuff like that. Yep. So why don't you try one here? A student fills a graduated cylinder to 25 milliliters with a liquid. She then drops a solid into it. The volume of the liquid in the graduated cylinder rises to 33.9 milliliters. If the solid had a mass of 63.5, what is the density? Okay, so let's take a look. So again, this is very similar to what we were just talking about. So we basically got a graduated cylinder there. Terribly drawn. And it has an initial volume there basically of 25 milliliters. We're going to take this solid here that has a mass of 63.5 grams. And we're going to drop it in here. And when we do so, we are going to see the liquid level there rise to a final volume of 33.9 milliliters. So again, we have a volume by displacement type of situation occurring. To find the volume of our solid, we're going to take basically the difference between the water level before and after. So the volume of our object in this case would equal our final volume, which is 33.9 milliliters, minus our initial, which is 25 milliliters. And again, in this case, if we do that, gets us 8.9 milliliters in this case. That's our volume. We obviously have the mass of the object, which is 63.5 grams. And we know density is mass divided by volume. So we now have both of the things that we need. We could go into our equation here, 63.5 grams divided by 8.9 milliliters. So 63.5 divided by 8.9. Going to give us a 7.1 grams per milliliter in this case. Once again, these units are not going to cancel each other out, so they both remain. The number remains with the top unit. I went with 2 sig figs, basically based off of which calculation? It is the last one that we did, which is the division, but really that was based off of the first one that we did here. So a reminder though, in this first one, we are subtracting, which means we should look at decimal places, right? So this has 1 decimal place and 1 decimal place, which means our answer here should have 1 decimal place like we got. This though has then, when we come to here, we're looking at significant figures. This is 2 significant figures, and that is 3 significant figures, which means that is how we ended up with our 2 significant figures. Yeah. Yeah, so usually always, I'll put it this way, it does matter because obviously if you do it the other way, you're going negative sign. And for this and anything typically that you go through this semester that you do final minus initial, you should always do the final one first minus the initial. Although you don't want a negative here in like 2 chapters from now, when we do something like the change in temperature, you may actually want the negative there. So you want to always do final minus initial when you're doing something like that. And in some cases, you may actually get like a negative number, not in this application, but like when we do energy. And that negative number, for example, when you do energy that comes from a temperature change is actually really important to tell you if the reaction, for example, is exothermic, gives off energy or absorbs energy if it's positive. So for that. So just in general, when you're kind of taking the difference of something, always finals minus initial. It's always the numbers you wanted to use. Other questions? All right, let's continue on here then. Here is again a table from your book of some of the density, and as I mentioned before, definitely they want you to know the density of liquid water. And as I mentioned before, if you do need it in a problem and it's not provided for you, that's pretty much a good number to go with. Just 1 gram per milliliter is pretty much what you're going to use. Obviously, as you can see here, everything on this side is higher than, or larger density than liquid water, which means they would sink. These guys here would float, right? Now, what happens if I put a bunch of different liquids into a graduated cylinder and they had different densities, right? And I put some type of solid object in there and it just kind of hung out right about there. That would mean the solid object is more or less dense than the top layer. Yeah, it's more dense because it's below the top layer, right? And this solid object then would be more or less dense than the bottom layer. It would be less dense because it's above it, right? Yeah. And by the way, the liquid down here, say there's a liquid down here, would be more dense than the liquid that would be up in that layer as well, right? So you could also look at different layering that happens in terms of the density as well. And some other factors could come into play to that, but you could also look at that. Any questions on that there? All right. And here again, just some more common things. Cement, right? Bone are more dense than liquid water. So why don't we try this one here? Let's say a student needs 150 cubic centimeters of salt for an experiment. The density of the salt is 2.16 grams per cubic centimeter. How many 1-pound boxes of salt should he buy at Okay, so let's take a look, see how you're doing. Again, we'll pull out the information. I see 150 cubic centimeters. That is a volume, right? So I got a volume of 150 cubic centimeters. I obviously have a density given to me here of 2.16 grams per cubic centimeter. And I want to know how many 1 pound boxes I need. So if you weren't sure maybe where to start, but obviously we're doing something with density, you can think about the density equation and think about what was given to you. You have volume, you have density, so mass seems like a pretty good thing to solve for. And that would get us from grams, and from grams we could figure out really the question of what we want. Now, you could definitely rearrange this equation, just pop in the numbers. Or you could take a dimensional analysis approach, which again will help you maybe if you're unsure of rearranging equations and stuff like that. You maybe don't even have to worry about rearranging the equations correctly. Remember that when you have any type of value, especially something like a density, for example, you could use it really as a conversion factor. And because it has 2 units, you could actually use it the way it's written, or if you needed to, you could flip it the other way and take a more dimensional analysis approach. And that's what I'm going to do. I'm actually going to take a more dimensional analysis approach here, which is I have 150 cubic centimeters. So now I don't even have to worry about rearranging this equation, right? All I have to go back is to my dimensional analysis and go opposites cancel, right? I clearly don't want the volume anymore. So that has the cubic centimeters on the bottom, and I could set it up like this. And at this point, I know the cubic centimeters are going to cancel. I'm going to end up with a grams, which is a mass. And the nice thing about this as well is I don't have to worry about should I multiply or divide because I just set it up dimensional analysis way, and I know always I'm multiplying the top and dividing by the bottom. So I take out maybe some error that could happen over here if you maybe are not so great at rearranging equations. And if you take this more dimensional analysis approach, again, it kind of does the rearranging for you if you just think about it by getting rid of the units you don't want and keep the units that you do want. So in this case, we'll take this, and obviously this would be the same answer you would get if you rearrange the equation and solve for it in that fashion. You will get 324 grams in this case. Significant figure-wise, really, if we were going to use this as an answer, that is 2 sig figs, right? And that is 3 sig figs, which we do have to look at in this particular case. And really, if we were going to give grams as our answer, which we really don't need to in this case, but we would want to take it to probably something like 320. What we really also want to do is sort of like an earlier question. We want to make sure that we do answer the question, which is not how many grams, right? But how many 1 pound boxes you need. And since a pound is 453 grams, one box will do the job. And you'll have a little left over for your fries, I suppose, right? If you need to put some salt on your fries or something like that. So um, that is a really good approach to take it and do a more dimensional analysis way. Clearly, if you were solving for mass, it would be volume times density, and you obviously could plug it in the numbers and you get the same answer. But again, I didn't have to worry about rearranging that formula. I didn't have to worry about should I multiply, should I divide. Again, it kind of just takes a lot of the guessing work out of it, and it works really well with sometimes some formulas that you may not have to really memorize formulas. And you just take a more of the unit approach to getting rid of what you want and what you don't want. Any questions on that there? That is chapter 2, I believe. Any questions on chapter 2? Okay, so we're going to talk about chapter 3. And chapter 3 is a pretty short chapter. We're going to talk a little bit about matter in this chapter and the different states of matter. So let's just talk about that to begin with. There are 3 states of matter that we deal with, which is solid. And typically in the solid state, we have things that are packed in there fairly tight to one another. They also possess pretty much not a lot of energy, and that's why they're packed in tight to each other. They don't have enough energy to move around each other or move a lot, and that is what will happen. That is a little bit different than when we get to liquid. And in the liquid state, we still have everybody fairly close to one another. The difference, though, again, in the liquid state is it's a little bit more fluid. So they have a little bit more energy, so they can move around from each other, and that's why obviously liquids pour, right, rather than solids just come out together, basically. And lastly, we have our gas state, which is a state of matter where everybody basically just starts to fly around from each other. They are no longer basically connected to one another, and they have a lot of energy at that point as they're moving around and flying around. Yeah. Yeah, we don't really deal too much with that in chemistry and stuff like that. No. Yeah, mostly in physics you'll get in that, but we don't really deal too much with that in here. Yeah. Now, when we look at these guys, and as I might have mentioned in an earlier lecture, I mean, that recorded one, but we'll go over it since it actually goes in this chapter. There are transitions of state that you should be aware of as we go from something from solid to liquid. That again is the process of melting. Like if you took an ice cube out of the freezer, it would just start to melt, right? If you feel bad about your ice cube melting, obviously you pick it back up as the liquid state, throw it back into the freezer, and you would go from liquid back to solid, and that is the process of freezing. If you go from liquid to gas, like you're going to boil some water there to make some pasta, that's the process of evaporation or vaporization. When you take like a hot shower and stuff like that, right? The mirror and everything in there gets pretty wet and condensation occurs as you go from steam back to liquid. And that is the process of condensation. You can go directly from solid to gas, skipping the whole liquid cleanup. And that is the process known as sublimation. Dry ice is an example of that. And again, a reminder, although it is called dry ice, is actually carbon dioxide, it's not water, basically. Super cold, burn yourself as well, yes. You could also go from gas, again, skipping the liquid cleanup, back to solid, and that is the process known as deposition. It's how they make like CDs, DVDs shiny. They deposit metals on top of them. If you ever seen a CD or a DVD, I guess these days, they don't make too many of them. And these are what are referred to as the transitions of different phases. Now, when we talk about melting and freezing, does this occur at the same or different temperatures? It actually occurs at the same temperature. So melting and freezing actually occurs at the same temperature. For water, for example, that is 0 degrees Celsius. And it really just depends on what's happening at 0 degrees Celsius, depending on what you're doing with energy or heat. If it's not until you get a little above 0 degrees Celsius that you actually transition to liquid water, not until you're a little below 0 degrees that you actually transition to solid ice. At exactly 0 degrees Celsius, you actually have both phases happening at the same time. Is what's referred to as being in equilibrium with each other. You have like ice crystals. You got a little bit of solid, got a little bit of liquid water sort of happening at that point. Same thing over here. This evaporation and vaporization or condensation, it does occur at the same temperature, and for water as well, which is a good temperature to know. That's that 100 degrees Celsius I think we saw the other day. That is, by the way, the normal boiling point of water. That is sometimes referred to as the normal freezing point or melting point of water, which is 0 degrees Celsius. Same thing at 100 degrees Celsius, at exactly 100 degrees Celsius. You have both phases happening at the same time. You got a little bit of gas, you got a little bit of liquid water happening. Not until you go above 100 that you fully transition into sort of gas, not until you're a little below 100 that you're back into liquid as well. That is also what's happening at the surface of any liquid, which is why when you spill something on the table, right, a little bit of liquid eventually evaporates, because at the surface of that liquid, you got guys jumping out of the liquid phase into the gas phase, and you have air blowing them away, which means they can't come back, right? That's also why if you have a lot of liquid in like a cup, it doesn't evaporate as quickly, right? Because even though you're blowing away some, there's a lot of water molecules below that hasn't got to the surface yet, and it hasn't escaped as well. Now, all these things are related to energy, which we'll talk about in the next chapter after this. But as we go from solid to liquid to gas, Those are all processes where you have to put energy in to do that. So if you think about the ice cube, it picks up energy from the surrounding air because it's actually colder than the surrounding air. And heat moves, as we'll talk about in the next chapter, from hot to cold. So because the room temperature air is actually warmer than the ice, it goes into the ice cube, and that's why it starts to just melt when you take it out, right? Also your ice cream as well. So when you do that and you have liquid water and you want to boil it to make your pasta, you put fire underneath it usually, right? Or heat, right? To boil it. And that is all processes that absorb energy. And those processes that absorb energy are known as being endothermic, as we'll talk more about in the next chapter. But endothermic processes are all processes where energy is basically being absorbed. Yeah, we will talk about that in the next chapter. We'll get into Q. Yep. As we go from gas to liquid to solid, those are all processes where energy is released. So if you think about gas molecules that are flying around, they have to have a lot of energy to basically fly around, right? Otherwise, they'll just fall. When they release that energy and lose that energy, they no longer have a lot of energy to fly around, which means when they come in contact with each other as they're flying around, they kind of clump together and drop into the liquid phase. And as you continuously remove that energy, they no longer even have enough energy to pass each other in the liquid phase, and now they lock themselves into kind of the solid phase at that point. And those are processes which are known as exothermic. Right? By the way, that is also why, as we'll talk about in the next chapter as well, when you put that liquid water back into your freezer to make ice cubes, the liquid water, which is room temperature, is now hotter than the temperature of the air in the freezer. So all the energy from the room temperature water leaves it. And now it becomes ice, yeah, and it freezes and makes ice cubes, basically. Any questions on any of that there? So when we talk about matter and the three states of matter there, matter again is anything that basically has mass and occupies space. So again, pretty much anything for the most part. As I just mentioned, there are three states of matter. Solid has a definite shape, and it's very rigid. So obviously, like the tabletop here, pretty solid. Let's say hello to him next door. That's pretty solid as well. And it's very hard to change. Liquid, on the other hand, doesn't have a definite shape. It will take really the shape of whatever container it's in, but it does have a definite volume. And what that means is if you had, say, 10 milliliters of water, and you took that 10 milliliters of water and you put it into a water bottle, it would take the shape of the water bottle. If you put it into that trash can over there, it would take the shape of the trash can. If you put it into one of those silly straws that go all the way around, it would take the shape of that. What we mean by a definite volume is if you had 10 milliliters in all those examples and you're not a klutz and spill it everywhere, you should still have 10 milliliters no matter where you put it, right? The volume won't change, but the shape will. Gas, on the other hand, because they are flying around, and something we'll talk about when we get to the gas chapter, because they are basically flying around in the container, we think of them as filling the container uniformly. And they're moving around in the entire volume. And that's what we'll talk about when we get into the gas chapter, which is one of the things that makes something maybe you heard of an ideal gas is the idea that the container's volume is much larger than the gas molecules themselves. So we think about the volumes container as like the volume of the gas that's present in those type of situations. We will get there. Yes, that is it. Other questions? So here you can see our liquid taking the shape of whatever container it's in. And here's also our three states of matter. And this is for water. And as we talked about a second ago, what happens with ice, ice is sort of over here. And water is held together with itself with something that we'll talk about in a later chapter, which is known as hydrogen bonding. And what happens when water hydrogen bonds, it is a bond between a hydrogen in one and an oxygen in another. And one of the important things in chemistry is the idea of opposites attract, and the oxygen in water is more negative, the hydrogen in water is more positive, and opposites attract each other, and that's how they come together. So as water comes together and it starts to sort of hydrogen bond with itself, in the liquid state, it actually has a lot more energy than it does in the solid state. So it's able to actually get a lot closer in the liquid state. But what happens when it gets into that solid state and has lost some of that energy, it creates all these big open spaces between the water molecules. And if we think about, to tie the last chapter into this chapter, the density equation we just did, right? If I create now something with a bunch of open spaces between the molecules, I now have a much larger volume, right? And that means my density is going to get smaller, right? So we will end up with a larger volume and a smaller density. And that doesn't happen in the liquid state. They could kind of get a lot closer. It doesn't create such a big volume for those water molecules. And that's why the density here in liquid water is actually larger than it is in ice. Question on that there. So again, from your book, a table of some of the values and stuff that we see there. Solid again, rigid, fixed shape and volume. Definite volume takes the shape of the container for our liquid and obviously our gas. The stronger the forces, the more rigid the matter is. And that is the idea. You have to always remember that, for example, when we talk about water, we're not just obviously talking about just one water molecule by itself, right? There is a ton of water molecules are all together. And in general, the way things are in terms of their state has a lot to do with how they can interact with themselves. So for example, something like water can hydrogen bond, which is a really strong interaction with itself. And that's why, for example, we see water as a liquid under normal conditions. Now, if you take something like what you'll do tomorrow in lab, when you light your Bunsen burner and you open up the gas line, that is methane. And methane is CH4, similar to butane or propane you might be familiar with as well. And all those things are quite flammable, right? And they're also gases. And they're gases because something like methane, when it's with another methane, is actually held together by a super weak force. And if you look at it wrong, it's just going to be in the gas phase, and it pretty much is in most cases going to be able to go into gas phase. Because in order for something like methane, for example, to go to the gas phase, you have to break that bond right between methane molecules to allow them to fly off into the gas phase, right? And go into gas phase. Same thing with water. In order to make water into the gas phase, you got to break those bonds, right? The bond between one water molecule and another. That's what you're doing, right? When you boil water, right? You break the bonds between the water molecules. They end up in the gas phase and they come off as steam, right? As it starts flying around and your water starts to boil. Takes a little bit harder to do with water. You got to get up to like 100 degrees, right? To kind of get it to do that. Methane, you definitely don't need to do that. It's just pretty much going to be that way. And same thing with like propane and butane. And those things are what are sometimes referred to as being very volatile, which means that they could go into the gas phase really easily because they're not held together very tightly. So things that have a really strong interaction with itself, a lot of times will be found in the solids phase. Things that have a really weak interaction with itself, oftentimes will be found like more in the gas phase. Any questions on that? That is the combustion reaction, which is basically what you're doing when you light your Bunsen burner tomorrow in lab. It's usually very flammable because they are a gas. A little spark will actually create fire, basically. As long as you keep feeding it with the oxygen, you'll continuously have that combustion reaction. It is what happens in your car if you have a combustion engine, not a maybe like a battery engine, but if you have a combustion engine that uses gas, that's what it is called, a combustion engine, right? You put gasoline in there, which is like methane. It's an organic compound. Oxygen comes in through your air vents, right? Spark plugs spark, right? You get energy, right? And that powers your car. Any questions on that? A little automotive there right before we ended. All right, let's end right here and let's talk about